Every year, a headline: new largest star discovered, UY Scuti, then Stephenson 218, then WOH G64, now RSGC1 F01. Scroll the comments on any of these videos and you'll find the same confused question, asked 1,000 different ways. Didn't we already crown this? None of those stars got smaller. None of them shrank overnight. What actually changed was how confidently we could measure them, and that story is far stranger than the ranking itself. The largest star title has changed hands more times than most people realise. VY Canis Majoris held it for years, a red hypergiant, so beloved that fans still defend it in comment sections today. NML Cygni took a turn. Then Betelgeuse briefly grabbed headlines, mostly because it's visible to the naked eye. None of these stars physically shrank when they lost the crown. Each time, a newer instrument or a revised distance simply produced a different number. Even Betelgeuse itself has swung in size estimates by hundreds of solar radii between studies, and it's one of the closest supergiants we have. The pattern repeats so often that it's worth asking a different question entirely. Not which star is biggest, but why astronomers keep disagreeing about stars they've already found. In 2012, astronomers pointed the Very Large Telescope's AMBER instrument at a red supergiant in Scutum, UY Scuti. Using interferometry, they measured its light directly and calculated a radius of 1,708 times the Sun, nearly 8 astronomical units across. A beam of light circling its surface would take almost 7 hours. Circling the Sun takes 14.5 seconds. For years, that number stood unchallenged. UY Scuti became the largest star known. Documentaries were built on it. Thumbnails were built on it. The number felt solid. It wasn't measured directly though. Not really. The star itself is too far, too dim, too wrapped in dust to resolve like a nearby star. Astronomers measured its brightness and temperature instead. Then they calculated the size mathematically. That calculation depends entirely on one number nobody had pinned down: distance. Then Gaia happened. The European Space Agency's Parallax mission remeasured UY Scuti's distance in 2018. The number moved, not slightly, dramatically. The new distance was closer, nearly 5,000 light years instead of 9,500. Plug a smaller distance into the same equation, and the radius collapses too, down to just 755 solar radii. Less than half the original claim. UY Scuti had, on paper, shrunk by 1,000 suns overnight. Except it hadn't moved an inch. Astronomers flagged the gay IA measurement itself as noisy, unreliable for a star this bright and this dusty. A later recalculation, using an improved gay IA data release, pushed the estimate back up to somewhere around 1,100 solar radii. Same star, 3 wildly different sizes, 0 physical change to the star itself. Here's the mechanic behind the chaos. Radius comes from one simple relationship: how wide a star appears in the sky, multiplied by how far away it is. Astronomers can measure angular width for nearby, unobscured stars with extreme precision, down to 1 or 2%. But red supergiants like UY Scuti aren't nearby. They're wrapped in shells of their own ejected dust, which blurs their true edge and scatters their light unevenly across wavelengths. So instead of measuring width directly, astronomers infer it from brightness and temperature, then multiply by a distance that might itself carry 50% uncertainty. Small errors in distance don't just add up. They multiply straight into the radius. A star doesn't need to change size to fall out of first place. Its distance estimate just needs to be revised. Nothing demonstrates that better than Stephenson 218. Discovered in a dusty, obscured cluster in Scutum, the star was assigned a jaw-dropping radius, 2,150 times the Sun. a volume nearly 10 billion times greater than our own star. If it replaced the Sun, its surface would swallow the orbit of Saturn. It briefly became the internet's go-to answer for the biggest star in the universe, the subject of endless size comparison videos, but the distance uncertainty behind that number exceeds 50%, and the radius itself sits well beyond the roughly 1,500 solar radius ceiling that stellar evolution theory says red supergiants shouldn't cross without becoming catastrophically unstable. Most astronomers now treat 2,150 as an overestimate, not a confirmed record. The star everyone screenshots might not even be the size advertised. There's a second layer of confusion worth clearing up, one that has nothing to do with distance. When astronomers quote a star's radius, they mean the photosphere, the visible surface where light finally escapes. They don't mean the enormous bubble of gas and dust that the star has already thrown off. Red supergiants shed huge amounts of material in their final stages, and that ejected material can spread across a region many times wider than the star itself. So a star with a modest photosphere can still sit inside a shell of expelled dust that spans light years. Confusing the shell for the star is an easy mistake, and it's part of why size comparisons on the internet so often disagree with each other. That 1,500 solar radius ceiling isn't arbitrary. It comes from something called the Hayashi limit, a boundary on the heart-sprung Russell diagram, past which a star can't stay stable. Push a star's outer layers too far from its core, and convection takes over from radiation. Gravity starts winning. The star can't hold that extended shape, so it contracts back down. It's the theoretical reason nobody expects to find a red supergiant at 3,000 solar radii, no matter how good our telescopes get. Every measurement that lands suspiciously above 1,500 should trigger the same reflex. Check the distance first before accepting the record. That single number, more than any telescope, is why biggest star claims get quietly walked back so often. WOH G64 offers a different kind of correction, one that came from actually looking. In 2024, astronomers used the VLTY's gravity instrument to do something no one had done before: directly image a star outside the Milky Way. What they found wasn't a clean sphere. It was an egg-shaped cocoon of ejected dust, asymmetric, possibly hiding an unseen companion star. The image suggested WOH G64 was dimming fast, maybe already shedding its red supergiant identity for a hotter, smaller, yellow hypergiant phase. That was the story going into this year. Then new spectra, gathered through 2025, complicated it again. The star still shows the molecular fingerprint of a red supergiant. It may never have made that transition at all. The most photographed star outside our galaxy still can't tell us definitively what it currently is. Which brings us to the current title holder for now, RSGC-1 F01, buried inside a dust-choked cluster 22,000 light years away, invisible to any optical telescope. Its radius, calculated the same indirect way as all the rest, lands between 1,450 and 1,530 solar radii, large enough to swallow Jupiter's orbit whole. It's a serious contender. It is not a confirmed champion. Every one of these stars occupies the same fog. Too distant to see directly, too dusty to trust completely, too dependent on a distance number that keeps getting revised. The truth is less satisfying than a leaderboard. There isn't a verified biggest star in the universe. There is just the current best guess, waiting for the next telescope to quietly rewrite it.